here we are in section 10.6, covering the short and sweet version of it today. Long story short, what's different in par mode, which is what you guys are just doing in your calculators, and I over here, strong window, was getting as well. We changed our mode to be par mode. We have our x's now being the t variable. We put in these equations that our notes told us to in function mode first up here and then in par mode down here. The main difference is basically there's this extra due t. Now, hold on. I actually want you to write, there is a third variable, always, 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 and it usually is t, but it sometimes could be, I want you to write or theta, which is going to be confusing because your calculator is only going to do t, but that's okay. In function mode, it only did x's, and every now and then we graphed something with t's instead of x's, and we were okay. Just a quick heads up, these functions, number one, they come in pairs, and you guys maybe realize we graphed an x equals and a y equals, not just one, but both. So first of all, parametric come in pairs. And second of all, both of them depend on another variable. These ones down here, I would have set equal to x of t and y of t. Instead of f of x, this one up here is f of x. That's okay. It's a function with x's inside. But these ones, x is a function with t's inside, and y is a function of t's inside. So notation changes a little bit. Notation changes a little bit, but also, if you guys notice, this one, this point right here, is where or what position some particle could have at time t equals 0. And then this could be the position based on these equations. There isn't just locations anymore. There aren't just x's and y's. There aren't just horizontal and vertical components. There's also now the possibility of when. There aren't just positions anymore. There aren't just where are you. Oh, I'm at this horizontal coordinate and this vertical coordinate. There isn't just a going over, going up. There's also a when are you there. So the when component is the t, because t could stand for time. Yeah, I was just asking that a second ago, so maybe you were just a little bit talking about it. Does it look like a line? It's like really far away. Okay, just look at it. All I did that was different. Go to x max being 100. Oops. We'll talk about the window in a second as to like the problems that can occur. So the long story short, we have this third dude, sometimes t, sometimes theta, and x depends on him and y depends on him, and they work together. Now, so the basics, before we just start troubleshooting our graphing calculator, because we're trying to learn the basics like by hand. When you first started learning graphs in Algebra 1, or maybe even pre-algebra, your teacher didn't say, get out your graphing calculator, let's use it. They were like, no, let's make a table, right? And usually it was like -2, -1, 0, 1, 2. And you plotted points. You were figuring out how to plug in x's. The very beginning of function notation of f of x. Plug in an x, get out a y. Plug in an x, get out a y. Etc., etc. So even though I just showed you this mode in your calculator, even though we're starting to see things like some people got lines instead of parabolas, and some people it was only graphing, well, all of us it was only graphing part of it, and maybe degrees radians have some sort of difference, etc. You really need to go back to the beginning and say, you know what? X is going to be a function in terms of t, and y is going to be a function in terms of t. Or, if it was the other way, it could be f a function in terms of theta. Or it could be g a function of theta. And every set of parametric equations, and that's why it sounds weird, every set has two equations, an x and a y. Horizontal and vertical. And basically, without you totally understanding what I'm about to say, parametric equations allow us to model two-dimensional motion and say x is changing and y is changing. Horizontal is changing and vertical is changing as time passes. To be honest, all we have to do is add a z of t in order to have the third dimension come into play. But we're not going to do that. We're not going to chapter 11. We're not doing three-dimensional motion or three-dimensional vectors. So here's how we do a table, because everything is just a little bit different now. Everything's just a little bit extra because we have this extra variable. Instead of just x's and y's, we actually have to start with t's. T is my independent variable. Both x and y depend on it. So we're going to make a table. And if they don't give me any t's, okay, I guess we'll do the -2, -1, 0, 1, 2. If they don't give me anything, I guess we'll start there, because that's where we've always started. But if they give me something like t is allowed to be in between -5 and 20, well, maybe we'll do -5, 0, 5, 10, 15, 20. We could change. Or if they say t is greater than or equal to 0, okay, 0, 2, 4, 6. But we're going to plot the points in order of increasing values of t. So we're going to plug in. I'll put after plugging in t values to x and y. We can't plug in points if we don't have points. And we're not going to have points unless we plug t's into the x's and the y's. And if they're thetas, whatever. We plug the thetas in into the x of theta, y of theta. So what's different and what's weird is, guys, the points that you're plotting, when I say plot points, they're only coming from these two rows that you're both filling in from formulas after plugging in t's. So we're not actually putting t is -2, -1, 0, 1, 2 on the graph at all. It's not a position. It's not a where. It's a when. So our points are our x's and our y's. Our t are just when they're there. Orientation is just a snazzy way of saying, and he's kind of an important word, you'll see him, the direction arrow. I'm going to technically say direction arrows. And we're used to direction with vectors, at least kind of, like an arrow points to the way it's headed, or the way the force is pulling, or the way the movement or motion is going. So we're doing direction arrows, but it's showing the orientation of the object's movement, or the direction of the object's movement. And how do we know what that direction is? Well, it's all based on, as we go from one time to the next, as we plot the points starting at earlier times, ending at later times. If we follow time, which only goes in one direction for us, we can know the direction of the movement. Say, well, as time passed, it went this way. I'm like, okay, cool. Draw me arrows to show me that. So we're back at the basics. We're not troubleshooting the graphing calculator anymore right now. We just know that the graphing calculator can do this. Let's go do something basic as far as practicing, just getting used to the general idea of parametric equations. So this direction says, sketch the curve given by the parametric equations. There are two of them. Of course there are. They come in pairs. There are two of them. Of course they are. They come in pairs. They gave me -2 to 3, so I started my time at -2. I'm ending it at 3. And I'm just going to go by ones to make life easy on myself. So guys, how would you fill in x and y if you knew that t was equal to -2? Which you're like, why is there negative time? Well, if right now is 10 o'clock-ish, couldn't -1 have been 9 o'clock-ish and -2 have been 8 o'clock-ish? You can go backwards in time as far as modeling. So don't think that we're doing time travel or anything specifically. It's not going crazy. But just -2. Okay, it could have a context. If this is like 10 a.m., that could have been 9, that could have been 8. If this was today, that could have been yesterday, the day before. Okay. But wouldn't we have to plug into x, -2? Wouldn't we have to plug into y, -2? Plugging into x, that'd be 4 minus 4, which is 0. Plugging in y, that'd be -2 over 2 is -1, right? So does it make sense why 0, -1 is in my table? Just plug it in, please. Get out x, get out y. Now how do I plot that position? I'm only looking here. So what point am I plotting, guys? Yeah, just 0, -1. Is it okay? 0, -1. No stress. Where does t equal -2 go? It doesn't. It's no big deal. If we need it, we'll think about it. If we don't need it, okay, fine. My position, my particle, my car, my person is at this position at that time. So how do you think the rest of this table is going to be formed? What did I do to -1? Plug in, got it. 0, plug in, got it. 1, plug in, got it. So let's go ahead and graph these points. I want you to go ahead and graph. I didn't want you to have to do all the math to the table. Let's just assume that you plugged in all the t's and you found all the points. Go ahead and plot these points, kiddos. Let's get a path. Let's see what this thing is doing and where it's going. Okay, so do we have to copy the table? Yeah, I would. Just so you get the idea of, okay, take t's, plug into x, plug into y. Now graph those points. In increasing order, don't just go haphazardly. I'll plot this one, I'll plot that one. I like this one. Go in order. Time moved from -2 to 3 this way, so you move from -2 to 3 in the same direction. What do you guys think? Kind of? Now, if I was to connect this, which is what your calculator did, which Matthew, maybe this will make some sense. When you tell, or when your window in your calculator shows, oh, we shut off. When it shows T min, T max, it's kind of like a table. Because you're telling it, start at this T value. Okay, cool, 0. Go to this T value, which is like 2 pi. But then in a table, don't you have to go by certain increments? I'm going by 1s, but what is my calculator going by? Because it can do a lot more math a lot quicker. 0.1. So how many little baby steps is it taking between here and here? Quite a few. Why? Well, if I was to go ahead and make it take fewer steps, let's say I went by 1s. Guys, how many steps would it, or how many points would it plot if I'm going from 0 to 6-ish going by 1s? Just 6 points. So does it make sense it's weird and fragmented? Because your calculator is literally saying, okay, fine, I'll find my 6 points and connect them. Ha, ha, ha. It doesn't know any different. If you change, look at my window. If you change the window, like a table, to say start at 0, go to 6, it's like the table we just made, except this one was from -2 to 3. And I'm telling the calculator to go by 1s. It doesn't know, make it nice and pretty and curvy, so it just says, fine. There's 1, there's 1, there's 1, there's 1. Now it has more down here, just it doesn't fit on the window. But it did 6 jumps. So just a second ago, Matthew had his going by jumps of 7.5, I think. And sadly, 7.5, well, it's not going to show. I think you actually had 360, didn't you? 7.5, it's going to say, well, 7.5 is way down here, so I'm just going to connect. It doesn't realize there were all these jumps in between. So some of you guys, I changed your window to be a lot smaller because it's a smaller increment of time, and to go by smaller steps, saying, wait, if you only check in, want a good analogy? Many of your moms, well, how many of you guys are driving? Are you good? That's it? Okay. My drivers, do moms get a little worried, especially when you first start driving, as to where you are and whether you're okay?
Yeah.
No, some of that's valid, right? Some of that's a little paranoid. But either way, so what do? Maybe now they have they can check your location, I get it. But think in the olden days before the app of Find My iPhone, right? Or share with friends your location, right? What would they have to do? And some of them still do. Call. Where are you? How are you? What are you doing? Is everything okay? Right? They check in with you if they don't hear from you. What if, let's just use this analogy. What if your mom only checked in every 7.5 days? Would they know where you are? How you're doing? Where you were those 7.5 days? No. Not unless you're like, overseas with me and the blog is being updated. But besides that, right? So just a second ago, when I was like, hey, let's check in every 7.5 days, they have no clue where you were in between. So what would a good mom do if they really wanted to know and didn't have GPS locators? Check in every 0.1 days, or maybe 0.05 days, or maybe 0.005 days, every 2 minutes, right? And be like, where are you? Okay, that's what the graphing calculator is doing. You're saying you can do this math really nice and easy, so can you just go ahead and plot exactly where you are? Because if you just jump to this future time, well, I don't know what was going on. If I only check in every 7.5 days, it's not a big deal. But I have no clue what happened in between. So that's just a silly little example. But if we're talking about time, if we want to know what something is doing, we want to check in multiple places in that motion or in that movement. So for us, this is totally enough because guess what? Because I'm not a calculator, even if I had my calculator do this, we could put in these functions. You're going to see your calculator do something really weird that it's never done yet this year. It's going to graph what looks to be a non-function. And I'm going to put little arrows saying, hey, I went in order, and as I went in order, this thing went this way. Because in a different example, it could be going the other direction. Because we're not moving by x's having to go from left to right. We're moving by t's, which can put things in circles or in rotations, or can have things going from left to right or right to left, or sometimes left to right and sometimes... Anyway, now that we're going by t's, we're actually going to be allowed to have paths that fail the vertical line test. Because t is my independent. All I need is at one time you to be at one position. I don't need at 1x for there to only be one y. I just need at one time you to be in only one position. Like if your mom checks in and says, that's interesting. You're at the movie theater and you said you were over at so-and-so's house. How did that happen? Right? A little bit of an inconsistency. So that would be an issue. It's like, no, at this time you're supposed to... Okay, so if there was one time when you were in two locations, which is impossible, that'd be issues. That'd be a non-function. But for parametric curves, all of a sudden, if it's only based on time, if you're in one place at one time, you're good. This thing can curve however it wants. We don't really care. You guys don't need to necessarily write this down. I do want you to fill in the blanks, though. Different parametric equations can have the exact same path, the exact same shape, but different timings. I'm going to put that in quotes because time isn't always exactly what we're doing. Remember how I said it could be t or theta? Well, let me zoom in on this. It looks to be the exact same, right, guys? The exact same beginning, the exact same end, the exact same arrows, using the exact same direction of motion. But what about the equations? They're different. Why? Who's going faster? The exact same path, they just have different timings, so their equations look different because who's going faster? Right. Yeah, the guy on the right only took the 3 halves or 3.5 seconds or minutes or hours or days, whereas this guy took 3 whole ones. Does that make sense? So as soon as the timing changes, the equations have to change because the equations are based on the time. So you can have the exact same graph, exact same path, with different equations, which makes everything a little bit complicated as far as, well, how do I know what a graph looks like if there can be tons of different equations for the same graph? Well, sometimes it's going to be helpful to ignore the t altogether and be like, well, I want to know what you look like, and I don't really know all the different possible t things that can happen, and I don't really want to make a table every single time. So there is this process called eliminating the parameter. If you're eliminating the threat, oh, you guys watch enough like drama TV shows or whatever. If you're eliminating the threat, what do you do? Yeah, usually you're killing it, right? But if you're eliminating the threat, you're getting rid of it, right? You're taking it out. That's going to be perfect for eliminating the parameter. Because guess what? You're getting rid of it. T or theta, it could be a theta. You're getting rid of T. You're taking it out. I'm going to put it in quotes, but eliminate, to take it out, to get rid of it, right? But there's a very specific way to get rid of it. The idea is to eliminate the parameter. We're taking our x of t, y of t, and we're trying to get back to the good old-fashioned who we're used to, f of x. Parametric equations are actually a really useful, really important tool in just like making math modeling with math more realistic to real life, two-dimensional motion, three-dimensional motion. But sometimes it's helpful to be like, can we just go back to what we're used to? And how we can do that is following these directions right here. We take an equation, and I'm going to say the x one because the x one for our purposes will almost always be the easiest. But we take an equation and we solve for t. Isolate t, meaning get it by itself. And my ones who are kind of like thinking about whatever, like spy movies or military things, you can kind of be like, oh, if you have a target, trying to eliminate it, then maybe you should get him by itself. Where he's not like surrounded and guarded. And anyway, long story short, get t by itself. Once you have t by itself, if you can get a double for someone, it's even better. So you can take the thread out and then replace it with something else that no one will ever know. Now it's all conspiracy theory. But anyway, long story short, if I can get t by itself, I can go ahead and use that expression for t to plug in and substitute to the other equation and say, oh, I know how t and x are related, so I can actually ignore the t and say y is equal to who squared? 4x squared. And all of a sudden I'm like, oh, it's a parabola. Oh, that's easy. It's a parabola centered at 0, 0, and it's kind of like stretched really high up because of that 16. It's a vertical stretch. Back here, you might have been like, maybe it's a parabola. It's a square. But this I'm way more used to. So if I'm just trying to figure out the path, it might be way more helpful to go ahead and ignore the timing. And the way we ignore the timing, eliminate the t, is to basically get him by himself and then plug each other. But sadly, some equations get a bit harder. At least as far as the math is concerned. So what if, I'll give you something like this. This dude says, sketch the curve represented by the equations. And that gives me a hint. And it's like, you know what? This table might be really gross. So maybe it's easier to think about who he would be without the t's. Hence this whole, hey, hint, 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 eliminate the parameter. But some of you are like, how? Well, guys, the y has t in 2 places, so forget that. That's going to be too hard. The x has t in only 1 place. Oh, good. And my directions say try to get x alone. Sorry. Try to use the x to get t alone. So couldn't I square both sides to get rid of that square root? Is that valid? Is that legal? To square both sides? How do you get t alone? You learned from me this year, if you see division in an algebraic expression and you have to somehow change it, what should you guys think of doing? Yeah. You could say multiply by the reciprocal. I was just thinking just multiply. Just get it out of there. Get it out of the division. Well, I'm just trying to get, hold on, we're not quite to the y yet. We're getting there. But for right now, we still have to get t alone. Before we get t alone, or until we get t alone, we can't get into the y yet. Wait a minute. Can't I divide by x squared now? And then, I know it's not pretty, but can't I just do a -1? So I have t by itself, except, yeah, squared. So I can divide by the x squared to the other side. I can subtract a 1. I could get a common denominator, but I'm not done yet anyway. Because what am I going to use this t in relationship to x to do? Go take them out. So I'm going to say, okay, y is equal to t. Who's t? This guy. Okay, fine. All over t, okay, this guy, plus 1. Oh, that's nice. What happens in the denominator? Ooh, how do I divide by a fraction? Okay, so one way is we could go ahead and do 1 over x squared minus 1 times the reciprocal, which would be x squared over 1. Or if you guys want to do my trick, I would multiply top or bottom. Sorry, top and bottom. By x squared. That would have been 1, and this would have been 1 minus x squared, which is exactly what's going to happen when I distribute. Oh my goodness, you got to be kidding me. This ridiculous set of equations way up here is really just a parabola shifted up 1? Yep, with really complicated timings. But do you see how this is so much easier than all of that? But in life, it can be helpful to have ones and not just squares. Just to give you like a little baby peek. Now, I don't even remember exactly when we're done, but I know it's... Remember how I said there could be t's or thetas? I'm going to show you what to do if thetas show up. Because if thetas show up, we're like, oh, get t by... There's not even a t. My hint with trig is plug, hold on, into a property. Because there's something cool called cosine squared of theta plus sine squared of theta equals 1. If I could get cosine, and if I could get sine alone, all of a sudden, I might not have much work to do before getting rid of the theta. With trig, you can use a property. That wasn't too hard at all. Bye, guys. Homework for tomorrow, the best you can. Might be a couple weird ones with theta. Just do the best you can to see if you can find a property to plug in.